Good morning. Welcome to Making Stuff with Chris DeHut. For today's episode, I'm going to try and make it quick, but I want to go over some comparisons between the Pico and the Pico 2. The Pico 2 came out within the last 6 months, maybe a year. I finally got my hands on one, and I'm in the middle of a big project here on the channel using the Pico W. And performance might be a problem, so I'm giving consideration now to possibly using the Pico 2. Starting out with the two chips look very much, or the two boards I should say, the Pico and Pico 2, look very much the same as each other. Nothing really major difference. You'll see a different connector here. That's more manufacturer difference, nothing big there. You'll see some differences in here. All these components look the same and are in different places, but from our point of view as a user, picking it up, putting it in a breadboard or whatever we're working on, it's all pretty much the same mechanically. Now, going back in history with a lot of computers, all the way back to the 8086 and through the 386, 486, Pentiums and all that stuff, the manufacturers would announce their new chip and computers would be built around it and tell you how great and wonderful it is, and it's got this many flip-flops and gizmos and gadgets and all this cool stuff. But to me, as primarily a programmer, all these years, a lot of that ended up just being a bunch of mumbo jumbo, and it really didn't make my programs run more efficiently or faster. I've always been a speed guy. So my comparisons, whenever I would get a new computer, a new chip, whatever the case may be, I would just put together a couple of example programs to run on the old and the new and look at what it's really doing for me. All the other stuff, if it's a feature that I need, great. But if it's just raw performance I'm looking at, this is how I've done it for the past almost 40 years, I think. So let's take a look here. This is going to be the test that I'm going to do to check basic general performance. I'm going to do adding, subtracting, multiplication, and division. Yes, it's a microcontroller, but a lot of what I create has math functions in it, and I use them. And the other thing that we do a lot of is call functions. So I have a function in here, perform some math operations. All I'm really looking for in this is it taking longer or slower for that function to be called and executed. That's what's going on here. And then the raw output speed of how fast I can turn an output on and then off. And we'll take another program to look at how fast the Raspberry Pi Pico can respond to an input by turning on an output. We'll be using the scope to look at that data. To start out with, I'm also covering the memory info output of MicroPython. I want to verify that in truth I'm going to get double the memory, double the storage, things like that. So let's just start diving into the results, and we'll cover it as quickly as we can. As mentioned, I'm not a big fan of all the razzle-dazzle, funny names and cute names and all that fun stuff. I want to know performance, so I'm not going into a lot of those sorts of details. But the old Pico was referenced as RP2040, that's the Raspberry Pi Foundation's chip. The new one is RP2350. Yes, it has meaning, and you can look at that in the data sheet and everything else. The chips, one's a dual-core ARM Cortex M0 Plus, the other's the dual Cortex M33. Means nothing to me. The clock speed, that one's always critical because that's directly tied to performance. At least in microcontrollers, it almost always is. In CPUs that are running on an operating system, That isn't always the case. As we've all seen, if you've been following and working with the evolution of computers since the beginning of time, we would get a new microcontroller or a microprocessor. We would load it up on our new computer with the newest Windows operating system or whatever it is, only be disappointed it runs a lot slower because of the operating system, not necessarily because of the chip. In our world in microcontrollers, it definitely does directly affect performance as we're running it. But I'm just looking at currently the clock's base frequency, meaning what it kind of comes delivered to you as. The Pico had 133 and the Pico 2 is 150 megahertz base frequencies. Here is the statement of what the memory is supposed to be. It was 264K of SRAM. Now it's 520 KB of SRAM. 2 megabytes of flash storage, 4 megabytes of flash storage. So basically twice as much. And to me, that's very important. Whenever I upgrade to a new microcontroller, I want more memory, more speed. Otherwise, what's the point, right? Now, there is one interesting actually, there's a lot of interesting features added to the RP2350, the Pico 2. But there's one that's kind of standing out that was a kind of a bummer to me on the first Pico, and that is low power sleep and dormant modes. It just didn't have a wow factor to it. So I'm really looking forward to diving into that when I get into some more of these battery-powered projects. So that's all the specs I want to go over from the propaganda sheets that are put out by the manufacturer. Now, out of the mem info output MicroPython command, this will tell us what is available and how the memory is currently being used, etc. And there's just a couple of things in there that I find very important, and it directly correlates to what we just talked about, the amount of memory. And that would be right here, this item, and this item, this being the Pico W, Pico 2W in the greenish color. And for those of us that are graphic, you'll notice that we've got a whole lot more memory. And I have been, a little bit of testing I've done, and I kind of loaded a bunch of big program in and added more to it and so forth. And it seems to be pretty happy with us using that memory. The math performance output, that really had no real surprises. Everything went up in efficiency. So first we'll look at the data, and then we'll just kind of briefly sum it up with the graphics. Now, the way I've done this comparison, I'm always comparing against the Pico W at 133 megahertz. And then I'm making a comparison to that. So when I say percent change, it's against that, not to the other clock speeds in the same chip, etc. So the Pico W at 240 megahertz overclocking, which is where I run standard. I've had great reliability with it and no problems. So to me, that's my default overclock. And that provided an 80%, approximately an 80% improvement over the 133 megahertz. Moving on, normally the Pico 2 will run at 150 megahertz, but I wanted a direct correlation, clock speed the same on the Pico original one and the Pico 2. Well, that didn't give me quite consistent changes there. It was more varied, not unexpected. When I go to the 150%, yep, now we're running faster than the original Pico 3. In both cases we are, but we're seeing more of a realistic improvement. Now when I go all the way up to the 250 megahertz, now I've been seeing reports, people running this thing upwards of 600 megahertz. That's insane. but there's special things you have to do with cooling, etc., setting the voltages, things like that. And I prefer to pull out of the box, overclock it to some point that's very safe, very reliable, and it doesn't require special attention. If I got a very unique project, I might need to do that, but for the most part, I want to stay in that safety zone for reliability. But we had some real nice 200% type of improvements on a lot of the capabilities. So twice as fast, to me, I love that. That is what I'm buying when I want to go from one grade of microcontroller to the next, or one model to the next, that's claiming higher performance. And the bar graph will help explain a lot of that, or kind of give you a visualization, I should say. We've got, starting out up here, actually let's go to the bottom. This is just basic, our baseline, subtraction. In other words, I've got a loop, and in that loop, all it's doing is taking a variable, subtracting from it 1, or some other slightly variant of that. And what I'm doing that as floating point math. To me, much of what I do with microcontrollers, I'm working with floating point math, so that's my baseline. The PICO W is in the blue at the bottom, so that would be this lowest line here. Then we go up to the PICO W at 240 overclock, to the PICO 2 at 133 is yellow, PICO 2 at 150 is green, and PICO 2W at 250 megahertz is this reddish brown color. And of course, here we're measuring time and we're looking at speed. So the shorter the bar, the better it is. And here you can see we've got really good performance improvements in every single one of these cases. So all around, it looked really good. The other thing that was interesting, division's always a problem with computers, and they can be a real time penalty. It's very much in line with multiplication on both the PICO and PICO 2. So I really appreciate that out of MicroPython and their implementation in the PICO. As we get into subtraction with string manipulations, let's get that shrunk down a little bit, and you'll notice that the times go way, way, way up. String manipulation is very slow in MicroPython and therefore also on the PICOs. But nonetheless, we still see tremendous improvement when we go from the raw PICO at 133 megahertz to the PICO 2 at 250 megahertz. So great performance gains there. Another one is subtraction and function calling. That is where I was trying to evaluate and do a comparative on how long it takes to call and execute a function. Is there a penalty? Did that get slower or did it get faster? In truth, if I look at it, no matter how I look at it, from the original 133 megahertz PICO, everything is faster. So no penalties were put in place there. It would be very rare to see that, but again, I want to verify it. And that was the purpose of this. The next one was basically I took that main loop that all it did was count down using a variable minus equals a floating point amount, took that loop and then added one more statement to it, and that was to toggle an output from on to off, back and forth with the toggle statement. And you'll see that again, we see great improvement. Everything behaved as expected, going faster and faster. So all around, all of these different things that I've done, worked out such that there is improvement without question and no penalties that I can see. Before I dive into the results of the next test, I just want to show you a few images that I grabbed off of the oscilloscope. This particular capture is showing the performance test where I'm turning on and off an input as fast as I can. And I did have some really nasty ringing in my first try at it, and I thought, well, maybe it was a bad breadboard, this, that, or the other thing. Turned out it actually was a breadboard that was creating the problem. So then I had to do this test on the same breadboard with both chips. But after I discovered that, this is what the waveform looks like as fast as it can go with going on and off through a loop. Nice square edges all around, looks really, really clean. And for reference, this would be we're at a 1 microsecond time scale, so that's 4.2 to 4.4 microseconds for on time. So about an 8.5 microsecond total cycle on that waveform. Pretty impressive, and it looks good and clean. For this particular test, what I was looking for was response time to an interrupt. So what I had set up on the Pico with a breadboard was I would have the Pico turn on an output that was the input to, that would be connected to an input via a wire for an interrupt request. That would then run its handler and then turn on another pin. And the time it would take from when I triggered that output signal to when it triggered the output signal, meaning doing or performing its action in the interrupt handler, that's what I was looking for. Because in the architecture and all the other stuff, these things can get very long or very short. Well, this is the data. It got better, plain and simple. Not necessarily magnificently faster, but it's faster. And here you're seeing 42 microseconds on the Pico 133 megahertz. Pico 2 at 250 megahertz was at 25 microseconds. It's still a very short period of time, especially when we're processing it the way we are. We all know the Pico is capable of much more using the PIO functions, but I'm avoiding that and staying within the controls of normal MicroPython. But how I measured that, going back to what the oscilloscope showed me, this is the rise of the output signal. Then we jump in between here and here is when we jump into the interrupt request, then its handler, and then we turn on the other signal. And that's how I measured it, so it's fairly accurate. All around, every test that I came up with and threw at it, we saw a performance enhancement. And that's what I look for when I see a new model of any type of computer device. Honestly, I don't really care about all the other stuff. It's great, it's wonderful, all the fancy names and the cool digits and gadgets and gizmos, wonderful stuff. But most of what I do with microcontrollers involves math, calling functions, and turning things on and off with the I/O. So to me, this is the most important aspects of the microcontroller that I'm after. So hopefully this information will guide you a little bit if you're in a performance challenge project with a Pico right now, Pico or a Pico W. The Pico 2 or Pico 2W looks like we can get a real serious performance boost without moving out into the super overclocking region where reliability gets to be a problem and things get a little too dicey. So hopefully this helps you out a little bit. I'll wrap it up at this point, and I look forward to seeing you in the next video.